So now we'd like to talk about learning curves, which is a really good diagnostic tool for understanding how model complexity impacts the cost function as we vary the size of the training set. And we're going to look at both the training cost as well as the test cost. And of course, to do this, we have to look at the expected amount of cost over different data sets that we could sample for either testing or training. So let's look at these learning curves with respect to both simple and complex models, meaning when we use a learning algorithm that's restricted to a small hypothesis set against one that has a more rich representation. Let's start with the simple one. On the left-hand side here, we can see how both training and test costs vary as we ramp up the number of instances. We can see a fairly large cost for both training and testing, and this is because the model is very simple. There's no way that we can match the actual target function given the simplicity of the types of hypotheses that can come about. Of course, as we increase the number of examples that we get from our target function, we'll be able to pick the thetas that give us the best hypothesis that could match the target function. So our test costs will go down overall as we get more samples. What's a little hard to understand is why our training cost goes up. So imagine if we only have a few examples, we're not going to have problems fitting those examples with the expressiveness of the hypothesis class. But as we get more and more data points, the weakness and deficiencies of our hypothesis set become apparent. We won't be able to fit the target function well. We can see that the gap between the training and the testing cost decreases over time. As we get enough samples, our training and testing costs should converge to basically this area, which is the expected best representation of the model, which we can think of as our bias. Right? So this is the error or cost due to bias. Let's take a look now at what happens in the complex model. In the complex model, we'll see right away that the bias error is a lot lower, right? And hopefully you understand why. It's because the hypothesis space of the complex model is much better able to represent our target function. So there should be a fairly large gap between the expressive power of the complex model as opposed to the simple model. You can see that gap illustrated approximately by this amount. And just like before, when we have very few data points, we can actually get zero training error. And this is because we have so many degrees of freedoms that we can just basically memorize the training data, just in the case of fitting 2 points with a first order polynomial, which is just a line, right? It can exactly get zero squared error on those cases. But as we get more data points, there'll start to be errors. And the problem with having few examples here is that we're fitting the particularities of the training set. So when we try to look at the test performance or cost, you can see it's off the charts, right? Even the red curve doesn't even show up for this region of the graph. Overall, when we get enough data points though, you can see that again, the test and the training performance will converge and we'll get better performance, and the generalization error that we'll have will be smaller because we have enough samples. Now these two graphs are at scale with each other. They actually illustrate a particular model of polynomial fitting, which you have a chance to look at in more detail. So the number of instances at any point on these two graphs are identical. So for example, roughly this part here would correspond to the same part here. And my question to you to think about, that we'll talk about in just a little while, is which part of the graph illustrates overfitting, right? We know that when we have too small number of instances, choosing a complex model like the one on the right side is probably a bad idea. So when can we say that there's a crossing between overfitting using a complex model as compared to a relatively simpler model? Think about it and you'll see this soon. So when we think of bias variance, it's very easy to put this on the learning curve, right? When we go to the asymptotic limit When the training performance starts to match the testing performance, right, that's the best average hypothesis that we can get that would represent the actual target function as viewed through the lens of an infinitely large data set drawn from the actual distribution of X. So we can understand that as the black line or the bias term. But to be able to select the correct hypothesis in that set is very difficult. And as we can see, when we have small samples, the variance is going to be larger. The variance is going to be illustrated by the gap between the black line and what we really care about, which is our testing cost. So that is going to shrink as we get more samples because our data set will be more rich and we'll be able to zoom in on which particular hypothesis or choice of parameters theta will give us our best possible hypothesis.